Good afternoon, statistics scholars, and welcome back to the next installment on our series from Chapter 5 of your text. In this chapter, we've been taking a look at how we can use the theory about the normal curve to help do statistical inference. In our first couple of videos on section 5.1, we explored properties of the normal curve, learning how we could use technology like StatKey to find areas underneath the normal curve. And we talked about how we could then use those areas and interpret them as p-values that could be then used to help decide the outcome for hypothesis tests. In section 5.2, we're going to again return to the normal curve and talk about how we can use theory about the normal curve to help to construct confidence intervals for unknown population parameters. Now, you may recall we've talked about confidence intervals before in chapter number 3. In chapter number 3, we used the theory of bootstrap distributions, and we took a look at how we could use percentiles of bootstrap distributions as the lower and the upper limits for confidence intervals for population parameters. That's one very fine approach that makes use of the power of modern high-speed computing. But there have actually also been other approaches for finding confidence intervals that have been around for generations. It's been known for decades upon decades that the sample statistics that we're often looking at, like sample proportions, tend to have these bell-shaped symmetric curves. And so long before bootstrapping became a thing, folks were using normal distributions to help construct confidence intervals. And in section 5.2, we're going to take a look at the theory of how to do that. It all begins with taking a look at the standard normal curve and finding certain special values, special z-scores, that can be used to guarantee a certain proportion of statistics between them. So to begin here, we're going to take a look at an exercise from your text, problem 35C from chapter number 5. In this particular problem here, the challenge is to construct, well, not to construct the interval, but to find the special z-scores, we call them z-star values, that would be useful for constructing a 96% confidence interval for a population proportion. Now you can see I've given the answer here that the values are 2.054 and negative 2.054. But how did I come up with those values? Well, I used my technology, my StatKey app for my standard normal curve. We brought up the theoretical normal distribution with a mean of 0 and a standard deviation of 1. That's our standard normal curve. And I've indicated that I want to take a look at a two-tail situation. The key thing here is we're looking for a 96% confidence interval. So what I've done is I've gone to the center here. There's a place when you choose the two-tail option where you can indicate what area do you want inside or between the two tails. In this case, I want 96% because I'd like to be confident that I've got 96% of all of the possible sample statistics between these two extremes. So StatKey allows me to go in to change that proportion or that area to be whatever I want it to be. Here I want it to be 96%. So I've changed the value to that. And now I go down and I look at the bottom and I observe what are the special values, special z-scores that will be sufficient to give me 96% of the area between them. I see from looking down here that they're positive and negative 2.054. What that implies is that if I want to make a 96% confidence interval, I need to use that many standard errors or that many standard deviations in order to construct a margin of error that is wide enough to guarantee the level of confidence that I'm looking for. That's the first key skill, finding these special z-scores that depend or relate to the level of confidence that you want. Now that we've found the z-scores, now that we know how to find them, let's apply that to actually find a confidence interval. I'm going to apply this in the context of problem 39 from your text. This wants us to find a confidence interval where the standard error comes from a bootstrap distribution that is known to be approximately normally distributed. Specifically, class, notice that they want us to construct a 99% confidence interval here. It's a 99% confidence interval for a population proportion. And they tell us that someone took a sample of size 200 and they found a sample proportion of 78%. That was their statistic. We've also been able to find through bootstrapping that the standard error for these sample proportions is 3%. Given this information, given the size of the standard error, given the sample proportion, given the level of confidence that we want to have, we want to construct a 99% confidence interval for the unknown population proportion. How does it all start? Well, it starts with the skill that we were just looking at a moment ago, finding the special z-scores, we call them z-star, that are needed to give us the level of confidence that we want. Now here, we want a very high level of confidence. We want to have a 99% level of confidence. So I went into stat key, I changed the proportion in the middle to be 99%. And when I did, stat key came back and it reported to me that the special z-score that I need, if I want to be 99% confident, I need to use a z-score of 2.576. That's my first step. But having found the z-score, I'm not done. That merely tells me how many standard deviations, how many standard errors I need to construct the margin of error that I want. My margin of error will always be my special z-score times the size of the standard error. I need to multiply those two together. In this particular case, my standard error was 3%, 0.03. So to find the lower limit of my confidence interval, I'm going to multiply my special z-score, 2.576, by 0.03 to find the margin of error. Then I'm going to subtract that from my known p-hat value of 78%. What do we get when we multiply 2.576 by 0.03? Well, my calculator tells me that that product is 0.07728. That product of z star times standard error, that is the margin of error for this confidence interval. It's a little bit more than 7.7%. I want to take that and subtract that from my sample statistic of 78% in order to find the lower limit of the confidence interval. When I do that, I see that my lower limit is about 70.3%, 0.70272. Now, if I'll take that margin of error and add it to the sample statistic, I'll get the upper limit for the confidence interval. So taking 78% and adding 0.07728 to it, I'll find my upper limit, which here is discovered to be a little bit more than 85%, about 85.7%. And there I have it. I have the limits of my confidence interval. How would we interpret this? We would say in the end that we are 99% confident that the population proportion is within the interval of 0.703 to 0.857. We're 99% confident that the unknown population proportion is somewhere between those two extremes. Let's recap again what the three steps were there. The first step, find the special z-star value that corresponds to the level of confidence that you want. Here, this was 2.576. Then multiply your z-score by the known size of the standard error to figure out the size of your margin of error. Here we did that by multiplying 2.576 by 0.03, and that gave us a margin of error of about 7.7%. Once you've established the margin of error by multiplying z star by standard error, we then subtract and add that value to the sample statistic to get the lower and the upper limits of the confidence interval. The lower limit is the sample statistic minus the margin of error. The upper limit will be the sample statistic plus the margin of error. And that is our essentially three-step procedure for finding the limits of a confidence interval. Let's finish up here with one final question. Question 45. Question 45 in your text asks for a confidence interval for a population mean. We want to find out what we think are values that we're 95% certain that the population mean falls between. Well, if we want to be 95% certain, we need the special z-scores that go with 95%. So once again, I've used StatKey. StatKey came back and told me that the special z-scores for 95% confidence are very close to 2. You might remember from back in chapter 3, we had a rule of thumb that if you wanted to be 95% confident, you used 2 standard errors. Well, that was actually, you might say, a little bit of an approximation. If we use our normal curve theory, we find out that to be 95% confident, we actually want to use 1.96 standard deviations. So very slightly less, very close to 2 standard deviations, but just a little bit less than that. Now we were told here in the problem that the standard error was 1.42. So if I multiply those two numbers together, 1.96 and 1.42, I'll find the size for my margin of error for this problem. When I do so, I discover that the product of those two numbers is 2.7832. That's going to be the margin of error in this instance for a 95% confidence interval for this unknown population mean. When we take that value and subtract it from the sample mean of 57.55, we get a lower limit of about 54.77 years. And if I add that margin of error to my sample statistic, I get a value of about 60.33 years. Those are the limits for my interval. Now, what was this an interval for? It was for an unknown population average, the average age at which folks gain admittance to an intensive care unit. So, in the end, I can make a statement of interpretation. Using the theory of normal curves, I have concluded that we are 95% confident that the mean age for patients entering an ICU is somewhere between my lower limit of 54.77 years and my upper limit of 60.33 years. Again, to reiterate our three-step process: number 1, find the special z-score that you need to guarantee the level of confidence that you want. Here that was 1.96. Step 2, multiply your special z-score by the standard error, z star times SE, to find the size of the margin of error. Here that was determined to be 2.7832. Once you've established the margin of error by multiplying z star by the standard error, simply subtract that value from the sample statistic to get your lower limit and add it to the sample statistic to get your upper limit. Then you have your confidence interval for whatever level of confidence you seek. And that is how we use the theory of the normal curve to help establish confidence intervals for unknown population parameters. I hope that this has been instructive, and stay tuned for another video forthcoming soon with further examples of developing confidence intervals using the theory of normal curves.